Hello everyone, welcome to my class. Today I'm going to cover the Dirac delta functions. Let me start right away. First, definitions. Delta functions, which is also called the impulse function. The delta function is a distribution function defined by the values of its integral. So delta t, we denote by delta. So delta t is defined as 0 if t not equals to 0 and infinite if t equals to 0, and the improper integral 0 to infinity of delta t is 1. So the diagram is here. At t equals 0, the spike outside 0 is 0. We can place delta functions over any value of t, means we are shifting. So delta of t minus a equals to 0 when t not equals to a, and at a t equals to infinite, and integral of delta t minus a over 0 to infinite is 1. So it looks like this delta function has a spike value at the point and outside is 0, but still the area is 1. Okay, so let's move on. Two properties for any continuous functions little ft times delta t equals to f0, and 0 to infinite of little ft times delta t minus a dt equals to f of a. Another way we can think of the delta function as the derivative of the unit step functions little ut. Little ut is defined as 0 if t is less than 0 and 1 if t is greater than or equals to 0. The graph is here. So its slope is 0 everywhere except at t equals to 0, where its slope is infinite. So this is the horizontal line, slope is 0. This is the horizontal line, slope is 0. But here slope doesn't exist. So that means u prime t equals to 0 when t not 0 and infinite when t is 0. So that's simply the function's delta t. Likewise, derivative of unit step function u t minus a with respect to t is delta t minus a, and integrals over 0 to t of delta t minus a, tau minus a d tau is little u t minus a. Great. Next, let's talk about Laplace transform of delta functions. Laplace transform of delta of t minus a is e to the power negative as. So put a equals 0, so the Laplace transform of delta t is simply 1. Similarly, Laplace transform of unit step function u t minus a equals to 1 over s e minus as. Great. So now let's solve some differential equations with Dirac impulse. Example 1. Solve y prime plus y equals to delta of t minus 1 with initial conditions little y 0 equals to 2. Start the solutions. Start taking the Laplace transform both sides of this differential equation. So the Laplace transform of y prime is this term inside this bracket plus Laplace transform of little y is capital Y of s equals to Laplace transform of delta t minus 1 is simply e to the power negative s, where the formula is here. And this formula is 1. Put the initial conditions and solve for capital Y of s, which is 2 over s plus 1 plus e to the power negative s over s plus 1. Then take inverse Laplace transform. So maybe one more comment here. This is the transformed one, this is not transformed one. So just use our Laplace transform table. So inverse Laplace transform of s plus 1 is simply e to the power negative t times 2 plus as it is. So to find the inverse Laplace transform of e to the power negative s over s plus 1, first don't worry about e to the power negative s. First find the inverse Laplace transform of 1 over s plus 1, which is e to the power negative t, and then multiplying the transform by e to the negative s means we are delaying the signal in the time. So delaying by 1. So then e to the power minus, in this one, t minus 1, and multiply by unit step function u of t minus 1. That's our second translation theorem. Great. Let's move on. Example 2. Solve y double prime plus 2y equals to delta times t minus 2 pi. Delta of t minus 2 pi with initial conditions y0 is 1, y prime 0 is 0. So the solutions, take Laplace transforms of this equations both sides. So Laplace transform of y double prime is this term inside the bracket plus 2. Laplace transform of little y is capital Y of s equals to Laplace transform of delta of t minus 2 pi is e to the power negative 2 pi s. Put initial conditions, factor the capital Y s outside and take other term to the right side. Solve for capital Y of s. So here capital Y of s equals to s over s square plus 2 plus e to the power negative 2 pi s over s square plus 2. Then find the inverse Laplace transform. Let's take the inverse Laplace transform. So the left side is simply little yt, and for the inverse Laplace transform on this right hand side, the first terms we can apply the formula easily, but for the second terms we have to manipulate. You have to multiply by radical 2 and divide by radical 2. This radical 2 comes from this denominator 2. So we multiply and divide by radical 2. So let's use inverse Laplace transform table to compute the inverse. So left side is little yt equals to inverse Laplace transform of s over s square plus 2 is cosine radical 2 t plus 1 over radical 2 as it is. Then now here, don't worry about first e to the power negative 2 pi s. So take the inverse Laplace transform of radical 2 over s square plus 2, which is sine radical 2 t, and then delay by negative 2 pi. So sine radical 2 now times t minus 2 pi, that's the angle for the sine, and times little u times t minus 2 pi. Great. I hope you understand this little computations here. Let's move on. Let's do example 3. Oops, that's better. Yeah. So solve y double prime minus 7y prime plus 6y equals to, here the step function and delta function mix on our right side. This is e to the t times little u of t minus 2 plus delta of t minus pi with initial conditions y0 equals to 0, y prime 0 equals to 0. So just the routine computations. Let's start the solution. Take Laplace transforms both sides of this equations. So Laplace transform of y double prime becomes this term inside the bracket minus 7. Laplace transform of little y prime is this term inside the bracket plus 6 times the Laplace transform of y is simply capital Y of s equals to Laplace transform of e to the t of step function little u t minus 2 is 1 over s minus 1 times e to the power negative 2s, and plus Laplace transform of delta of t minus pi is simply e to the power negative pi s. Next, put the initial conditions and solve for capital Y of s. So this is just the s square from there, negative 7s there, 6 there, and then take other term to the right side, but all terms are left side is 0, so only I have a right side as it is, 1 over s minus 1 e to the power negative 2s plus e to the power negative pi s. Next, now let's do this one here. A lot going on here. So the solve for capital OFS. So capital OFS equals to e to the power negative 2s over s minus 1 square times s minus 6 plus e to the power negative pi s over s minus 1 times s minus 6. So I'm in this step now. Then we use the partial fractions to simplify this fraction. So e to the power negative 2s as it is. The partial fraction of this fraction is a over s minus 6 plus b over s minus 1 plus c over s minus 1 square plus e to the power negative pi s as it is, d over s minus 6 plus e over s minus 1. Here the term is repeated, so we need to add one more constant, but here no terms are repeated in my denominator. So then, where a, b, c, d, e are constants to be determined, so I skip the partial fractions and the computations here, but it turned out to be this following. So a turned out to be 1 over 25, b turned out to be negative 1 over 25, c turned out to be negative 1/5, d turned out to be 1/5, and e turned out to be negative 1/5. Great. So then in this last expression here, now I am here, so let's take our inverse Laplace transform. And always keep in mind, multiplying the transform by e to the power negative 2s means we are delaying. Okay. So let's talk about here. Don't worry about this multiplying by e to the power negative 2s at the moment. So the inverse Laplace transform of 1 over s minus 6 is simply e to the 6t. Inverse Laplace transform of 1 over s minus 1 is e to the t. Inverse Laplace transform of 1 over s minus 1 square is t times e to the t. Similarly, here is inverse Laplace transform of 1 is 1 over inverse Laplace transform of 1 over s minus 6 is e to the 6t, and inverse Laplace transform of 1 over s minus 1 is e to the t. Then delay by pi in this expression, delay by 2 in this expression. Great. So the final answer is then little yt equals to 1 over 25 e to the power 6 times t minus 2 times multiply by step function u t minus 2, which is outside here. Similarly, second term, negative 1 over 25, inverse Laplace transform of 1 over s minus 1 is e to the t, delay by 2. So e to the power t minus 2 multiplied by unit step function u t minus 2 minus 1/5. The inverse Laplace transform of 1 over s minus 1 square is simply t times et, delay by 2, so 1 over 5 t minus 2 times e to the power t minus 2 times multiply by unit step function little u t minus 2, which is here. So I factor out these unit step functions. Correct. So then this plus is this plus. Similarly, 1/5 inverse Laplace transform of 1 over s minus 6 is e to the power 6t, delay by pi. So e to the power 6 times t minus pi multiplied by unit step function u t minus pi, which is outside. Wow. Similarly, negative 1/5 inverse Laplace transform of 1 over s minus 1 is e to the t, delay by pi. So 1/5 e to the power t minus pi times multiply by unit step function little u of t minus pi. I factor out. Great. I hope this makes sense here. So now heads up, in our next lecture we will cover system of linear equations of the form a vector x equals to vector b for Laplace transforms. So we finished this section 7.5. Thank you.